Any questions about anything before we start?
Can Markov chains be modeled as arrays, or are they modeled as arrays?
Arrays?
Arrays like matrix.
Oh, arrays.
Yeah.
Yeah, the question is, can a Markov chain be modeled using matrices? When you have a finite number of states, the transition probabilities fit together nicely in a matrix, and there's that whole relationship between the pi of n and pi of n plus 1, you know, all that kind of, we talked about that before. It's in the handout, so. Yeah, apparently one version of Math 2940, according to Matt, had talked about Markov matrices a lot.
Yeah.
When you took it from Ramakrishnan, but others didn't, so some people probably saw them before and some people didn't. How many people saw like Markov matrices when they took their math class, their linear algebra class? No? No, but linear algebra, I'm talking, no, okay. Yeah, I know 3100. Okay, well, we're talking about this Metropolis algorithm. And let me just remind you about that. And this is a really, really important item in the whole history of random algorithms and search techniques and all that sort of thing. And remember, it originated at Los Alamos, where these guys were working on life-threatening problems in statistical mechanics, as evidenced by that book. But anyway, the point is you have, you're looking at stat mech problems, and your goal is to figure out what I called E sub p Boltzmann of F for a variety of quote-unquote physical quantities of interest defined on this overarching reality of statistical mechanics, which is phase space, set of all positions and velocities of a bunch of molecules, say, in a box. And here p beta is equal to the Boltzmann distribution, or canonical ensemble, as they call it in statistical mechanics. And all that's known about p beta is this general functional form of it. And so p beta of some x in phase space is equal to some normalization constant times e to the minus e of x over kt, where t is the temperature, k is Boltzmann's constant, and e is the energy. E of x is equal to the energy of state x. So that's the background. And so what Metropolis et al. Did was they let capital S be some fixed discretization of phase space. Okay, so you can enumerate the elements of S. You can think of them, if you wish, as you can order them somehow so that they look like the typical state space of a countable state Markov chain with an infinite number of states. Okay? And actually in real life, it's always going to be finite, but whatever, just think of it as infinite for now. All right? And so what you're going to do is you're going to look at this p beta, and that sort of induces somehow a distribution that I'm going to call pi beta on S. And pi beta of state J is going to be equal to some constant. It could be the same constant or some other constant times e to the minus e of j over kt for j in the state space S. And you can imagine e of j might be the average energy over the little box that you label as state j. C0 might be whatever, just some minor adjustment of this C0. But I'm just going to worry about that as being the functional form. Okay? Now, here's the algorithm. Here's the statement of the algorithm. We had this on the board at the end of class last time. And there was a slight confusing thing in there that I want to fix today. So here's the algorithm description. And first I'll describe the algorithm, and then I'll tell you what it does, and then I'll prove to you why it does that. Okay? So what you're going to do is, your goal is going to be, you're going to assemble a big multi-set, and I'm going to call it script P. And script P is supposed to connote population of points in S. And you do that as follows. First of all, you initialize by picking some theta 0 in S and putting it in P. So now P has one thing in it. And then assume you've chosen theta 1, theta 2, theta 3, theta 4, and so on up through theta n. So assuming you've chosen theta 1, theta 2, up through theta n, and put them into P, you choose theta n plus 1 as follows. First, what you do is you propose a possible next theta, and I'm going to call that psi. Okay, so this is the proposal step. What you do is you perturb your theta n, say uniformly over some notion of neighborhood of it. This is kind of a user choice. We'll get into later on the impact of making different user choices on this thing of theta n to get psi sub n plus 1. This is the proposal for what theta n plus 1 is going to be. Once you've proposed psi sub n plus 1, you do the following. This is the accept/reject step. If psi sub n plus 1 has lower energy than theta n, so if E of psi sub n plus 1 is less than or equal to E of theta n, you quote-unquote accept the proposal. That is to say, you set theta n plus 1 equal psi sub n plus 1 and throw it into P. If, on the other hand, psi n plus 1, the proposal, has higher energy, you may accept it or you may reject it. You accept with probability e to the minus the difference between these energies, whatever it takes to make this exponent negative. So it's going to be E of psi n plus 1 minus E of psi n. So you flip a coin that has that as its heads probability. And in this case, you let theta n plus 1. You set, so theta n plus 1 equals psi sub n plus 1, and throw it into P. And you reject with 1 minus that probability. So 1 minus E of psi n plus 1 minus E of psi n. And in this case, the rejection case, what do? You set theta n plus 1 equal to theta n and throw another copy of theta n into the multiset P. Thus, in effect, you're quote-unquote adding another copy of theta n to the population P of points you're assembling. And you keep doing this. You go through the proposal step and accept-reject step for every n, building up. Every time you do this drill, you add another point to P. You might be adding the same point again and again and again. You might go away from that point and then someday come back to that point and keep adding it again. You know, it's all kinds of things going on there, but that's how you assemble your P. Now, on the board last time, I think I jumped the gun and I moved into IJ notation too early. So I said if E of j is bigger than E of I or something like that. But what I meant was this. Okay, that's the raw statement of the algorithm. Robert. Oh, theta n. There, sorry. And that should also be theta n. So still a mistake, but now fixed. Paul. Oh yeah, you're right. Over kt. Sorry. Thank you. So that's a description of the algorithm. Now what does it do? What does it do? If you remember our lead-up discussion to this, I tried to sell you on the idea that sometimes from a strong law of large numbers approximation standpoint, it's desirable to be able to draw a population of points from a set that's distributed according to some distribution you know. And as it happens, what this does, this set P, it turns out, over the long haul, asymptotically, P contains points in S that are distributed according to pi sub beta. And in that sense, what we've done is we've accomplished the mission that I said last time was desirable to do sometimes. If you have a probability distribution over set, generate a set of points from that set that are distributed, that are arrayed according to that probability distribution. Okay. You have a question? No? Okay. Andrew.
When you figure probability to accept if it's a greater value, if you jump up the mountain or whatever, is it always the multiplication of the two values together? Because that's just multiplication.
That's right. We're going to see that, yeah. This algorithm and its generalization by Hastings, it's always going to be the ratio of probabilities, so to speak. Now, one hint of a cool thing about this is notice that the C0 doesn't matter, this normalization constant we could not figure out. It doesn't matter because all you're doing is you're taking a ratio of this of psi n plus 1 to this of theta n, and the C0s cancel. So, in fact, all you need to know is not the distribution according to which you want to draw, but the functional form of the distribution according to which you want to draw, up to a normalization constant. Okay, now why? Why is it true that P contains points in S distributing according to pi beta? So how are we going to show this is true? So to see this, and that's one of those popular three-word euphemisms for proof. Okay. What we're going to do is, first of all, note that the Metropolis algorithm, what it does is it defines a Markov chain with state space S. That's the first thing we're going to note. Now, why is that the case? Why is that the case? Well, you think of theta n plus 1, or theta n, as the state of the Markov chain at time k. Or a state at time n, I should say. And think of P as the set of states you visit on a run of the Markov chain. Starting from theta 0. And this set of states you visit is generated by a bunch of random things that happen along the way, but the random things happen in a Markovian fashion. If you know theta n, you can figure out from this algorithm description the probability that theta n plus 1 is equal to any other state. And that's independent of what happened before. So this is Markov. So it's Markov because whenever you have the probability that theta n plus 1 equals j given theta n equals I for some I and j in the state space S, is determined by the description of the algorithm and doesn't change if I give you any information about states before time n. So it's given by the algorithm description and is independent of the history, theta 0 up through theta n minus 1. And I'll put independent in quotes because I'm not really using that in a technical sense, as in independent random variables. Okay, the point is it is a Markov chain, and it's fairly easy to see that from this. Okay, so this Markov chain, and it's homogeneous, it's time invariant. So note also, the Markov chain is homogeneous. How you pick theta n plus 1, given that you know theta n, does not depend on n. You do it the same at any time. All right, so all the theory we've developed applies to this Markov chain. Now, the cool thing is, it turns out, so as it happens, pi beta is a stationary distribution for this Markov chain. And if we make appropriate assumptions on the perturbations, the proposal step Q, and we think of S as actually being very large and finite, and this is something we're going to show. We're going to show this in a second. Assuming that the state space, remember, S is a fixed discretization of phase space in statistical mechanics, and so you think of it as being a bunch of contiguous little blobs in phase space. And by perturbing randomly around a neighborhood of any blob, you can get to another one. And if there's any two blobs, you can get from one to the other by some sequence of perturbations. And for that reason, this Markov chain is going to be irreducible. So with a suitable definition of the proposal step, this sort of uniform perturbation, the Markov chain turns out to be irreducible. That is to say, you can reach any other state, any state in finite time from any other state with positive probability. You can even reach a very high energy state from a very low energy state with positive probability if your coin flips happen to come up accept, 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 accept all along the line. Thus, if S is very large and finite, we know what? We know what about an irreducible Markov chain that has a finite state space? We know it has a unique stationary distribution. Its whole state space is one big old recurrence class. So the whole of S is one big, necessarily positively recurrent class. Positive recurrence class. And there's a unique stationary distribution. The chain has a unique stationary distribution. And by the fact that pi beta is a stationary distribution for this chain, pi beta is that unique stationary distribution. Let's call it pi star. And so pi beta equals pi star. And by all our results about the asymptotic fraction of the time you visit states reflecting the unique stationary distribution in such an irreducible finite state Markov chain, that's why the points in P are distributed according to pi beta. So all our results are theorems about the asymptotics of nj over n, nj of n over n, guarantee that the points in P are distributed asymptotically according to beta, or according to pi beta, which is the assertion I made at the top of the leftmost board by the international dateline. Maybe we should alternate classes and have this be the international dateline, that be the primordian on Thursday, say. Okay, is this a toll-free number calling me? No. It's a burn phone. It's 855, so yeah, that is a toll-free number. Therefore, I will not answer. No, I wouldn't answer anyway. I would. Even if it was my mom, I'd call her back during the break. Okay, all right, so this is why the points are distributed according to pi beta, because pi beta is the unique stationary distribution for this Markov chain, and we know that typically the runs, and of course all this is with probability 1. It's not, certain to happen, but it is almost certain to happen. With probability 1, the fraction of the time you visit state j is equal to pi, the stationary distribution amount of weight that assigns to state j, which is pi beta assigned to j. And by the ergodic theorem for Markov chains, and this is where Metropolis and company really wanted to apply this result, and remember the ergodic theorem for Markov chains, that applies to chains just like this, that have a state space that constitutes one big positively recurrent class and that has a unique stationary distribution. So by the ergodic theorem for Markov chains, for any function f from the state space to the reals, and think of this f as being a physical quantity of interest. Okay. So it's actually a discretization of such a thing. So these physical quantities of interest that were at the core of what they were trying to do to begin with we have the following. That with probability 1, the limit as n goes to infinity of 1 over n sum from m equals 1 to n, f of theta m is equal to e pi beta of f, which is roughly equal to e p beta of whatever, say f tilde is like the undiscretized, and I'll violate this boundary just for this one thing. And that's what they originally wanted to calculate, quantities of that kind. Okay, now what are some bonuses here? I'll get to those later, but let me just point them out now so you can keep them in the back of your mind. We could, if we wanted to, just assemble P. Make a big old set P, throw things into P without regarding the order we're doing it, and blah, 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 and then calculate averages by averaging F over P. But what we're doing here with this algorithm is we're creating the points in P recursively. Markov chains are things that computers love to run. Once again, anthropomorphizing computers. We're generating recursively, and we're generating recursive approximations to the quantity we wanted to find over the long haul. So you might have some stopping rule, like when the nth and the n plus 1th terms for 50 steps are within 0.01% of each other, you stop, something like that, because you've essentially converged. But the point is, this is generating a recursively generating an approximation to the quantity we want to find. Okay, so let's go back and see why. This is the big math problem we have to solve. Why is pi beta a stationary distribution for this Markov chain? Okay, so let me just circle that, even though I'm going to erase it momentarily. So that's the one remaining detail. Not really a detail, it's a big, huge thing. Details can be big, huge, right? Einstein said God is in the details. Some people say the devil is in the details. You know, two sides of the same coin, I suppose. So here's the big remaining question to answer. Why is pi beta a stationary distribution for this Markov chain? The Metropolis chain, so to speak. Let's see how this works. Let's back off and think about an arbitrary Markov chain, homogeneous Markov chain. So suppose you have a Markov chain with probabilities P of ij. So that's a very brief statement that that's the set of all transition probabilities from state I to state j for a Markov chain. Pi bar is a stationary distribution if and only if, so precisely when, pi bar sub j is equal to the sum from I, or over I in the state space S, of P of ij pi, or let's put it this way, this is the way most people write, pi bar I, P of ij for all j in the state space S. That's the definition of what it means to be a stationary distribution. That it persists, and think back to the marbles in the bins, right? This is how it evolves over time. That's what a stationary distribution satisfies, and anything satisfying that that's not negative and sum to 1 is a stationary distribution. Okay. Now this is called, this equation here is called the balance conditions on pi bar. So terminology, and let me give the equation a name. Well, I won't give it a name just yet. This is the balance condition or conditions on pi bar. And for obvious reasons, that's why it's called balance, because in some sense what goes in and what comes out of the sand, you know, that kind of thing. Now we can rewrite this as follows. First, note that if I do this, if I take the sum over all I in S of P of j comma I, what do I get for any j? 1, yes. So this is equal to 1 for all j in the state space S. So with impunity, I can multiply the left-hand side of this equation with that. So thus we have, and I'm going to flip the order of the right and left here, because that's the customary thing to do, the sum over I in S of pi bar I, P of ij, equals the sum over I in S, P of ji, all that times pi bar j. And this is a sum over I. Pi bar j doesn't depend on I, so I can just pull it into the sum. And I get this. So we have the equality of the two terms at the end. And that's going to be true if and only if pi bar is a stationary distribution. And that has to be true for all j. Now I'm going to give it a name. Remember I said I didn't want to give it a name just yet? So I'm going to call it star. Now the equality between the two underlined terms is an equality between sums over I. One way for that to be true is for the summands to be equal term by term. That's not the only way, but it could happen. Okay, so observe that one possible way for equation star to hold is to have these sums over I equal term by term. So have the sums over I equal term by term. That is to say, and I'm going to give this one a name double star, the ij, so it's going to be pi bar I P of ij equals P of ji pi bar j for all I and j. Now that is not the only way to have the balance condition satisfied. That's a really strict condition on the pi bars relative to p. Terminology. This equation double star is called the detailed balance condition on pi bar. So you have the balance condition, which holds for any stationary distribution, the detail balance condition that doesn't necessarily hold for any stationary distribution, but if pi bar satisfies this, star star, then pi bar is stationary, not the converse. Okay, so let me put that in big all caps, not the converse. This is only one special way to satisfy the balance conditions, which are equivalent to pi bar being stationary. All right, now that we've done all this work, what we're going to do is we're going to figure out the P of ij for the Metropolis Markov chain, and we're going to show that the Boltzmann pi satisfies the detailed balance conditions, from which we will conclude that the Boltzmann pi is a stationary distribution for the Metropolis Markov chain. So what we're going to do, goal, is first of all figure out the P of ij for the Metropolis chain, and then show that pi beta satisfies the detailed balance conditions double star, and conclude that pi beta is a stationary distribution for the Markov chain, and therefore the only one if it has only one, which we assume Q of ij is such that blah, 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 all that. Okay. So we conclude that pi beta is a stationary distribution for it. And that's the question we asked up there. Yep.
So intuitively speaking, for a stationary distribution, pi times the transition matrix equals pi.
Exactly.
But why is that part coming saying that, you know, pi times p equals p times pi? Like, I don't know.
Well, this is P of ji, remember. It's not, it's
a single term.
Yeah, for every I and j, this holding is one way for this to hold, is what I've proven to you on these boards. Okay, this can hold without having those sums, these two I sums equal term by term. That's why we call it the balance conditions versus the detailed balance conditions. An arbitrary stationary distribution will not satisfy the detailed balance conditions. It will satisfy this always. In fact, anything satisfying this is a stationary distribution.
So this is a more stricter constraint on a stationary distribution. Like
Yes, very much so. Extremely restrictive. Yeah. All right, so let's figure out the P of ij for the Metropolis chain. How do we do that? Andrew.
Is this just saying that between two nodes that the probability of going, taking a path from one to the other equals probability of taking a path from one to the other given any condition that we're in?
It's not quite that because like without those it would be that.
Right.
But with those it's not. Like going from a higher energy to a lower energy state is not going to have the same probability as going from the lower energy to a higher energy state. Okay. All right. So anyway, let's figure out the P of ij. So what is P of ij? What we're going to do is we're going to model the proposal step and the accept-reject step separately. Okay. So first, what we're going to do is model the proposal step as probabilities Q of ij. So as follows. Probability that psi n plus 1, the proposal, is equal to j, given that theta n equals I, is going to be Q of ij for all I and j in the state space S. So this, remember, arises from some kind of random perturbation, uniform perturbation over some notion of neighborhood around state I. That's how I make my proposal of the next theta. So let's model that as Q of ij. Now, assuming symmetry on the neighborhood structure, which we always do, Q of ij is going to be Q of ji. It's going to be reversible that way. Okay, so this is a step toward answering your question, or what I think your question is. All right. So, assuming reasonable symmetry, vis-a-vis, or let's not be pedantic, with regard to, or with respect to, so the neighborhood notion we have that Q of ij is equal to Q of ji for all I and j in the state space S. Matt?
Can you really make that assumption though? Because like if you have a box.
Yeah, I know. You're going to have edges. I know. But they always do. They make it. So let's assume that we don't care about the edge effects and we close the box on both sides like a torus, a multi-dimensional torus, like a video game, where it goes in one side. You know, if it goes out this side, it comes in this side at the top. You know, that kind of thing.
Okay, Pac-Man.
Yeah, Pac-Man-ish kind of thing. Yeah. I mean, the thing is, and then if you really want to be careful, you can just say, oh, well, we don't care about what's happening at edges, and asymptotically that goes away. We're only caring about what's in the middle and whatever. But this is what they always do. They always assume this. Okay? All right. That's the proposal step. Now the accept-reject step. So the accept-reject step, what we do is, if E of j, if you propose j from I, if you start in I and propose j, and E of j is less than or equal to E of I, in other words, j is a lower energy state from the one you started with, then you accept j. Thus, we have the following. P of ij, the probability of transitioning from state I to state j in the Metropolis chain, is equal to Q of ij when E of j is less than or equal to E of I. The probability that the next state is j is just the probability you proposed j, because j has lower energy, and if you propose it, boom, you move there. Rahul.
Therefore, if you propose that j is 1, then the probability of you going to j will be 1.
Yes, but we're assuming the probability is not going to be 1 for this Q. It's some huge set that you're perturbing around uniformly in a neighborhood. Yeah. So, what?
It's an equal sign, right? Or is that a not equal sign?
Where are we? This isn't equal. Yeah. Yeah, there was a lingering slash. Let me finish this, and then I'll try to address your question. Okay, so accept-reject step. If you start an I and you propose a state of lower energy, you accept it. Therefore, the P of ij for that pair I and j is going to be Q of ij. If you start an I and propose j and get something of higher energy, so if E of j is bigger than E of I, you accept j with probability what? E to the minus E of j minus E of I over kt. I won't forget this time. Whoever helped me out with that. But what's that? That's, if you think about it, that's just going to be pi beta of j divided by pi beta of I. Okay? Thus, in that case, if you propose a higher energy state, P of ij is equal to Q of ij, the proposal probability, times the ratio of these pi betas. when E of j is bigger than E of I. Now we're going to use these factoids. These are the two formulas. This gives us the P of ij for all states I and j in the Markov chain. And what we're going to do is we're going to show that pi beta satisfies the detailed balance conditions. Double star. That is trivially going to be true. Well, no, let's be careful. So thus, I'm going to consider two cases. If I and j have the same energy, and then I'm going to have it when I and j have different energies. If E of I equals E of j, P of ij is equal to Q of ij, which is equal to Q of ji by symmetry of the Q, which is equal to P of ji, because E of j and E of I are the same. And therefore, trivially, since pi beta of I and j are the same in this case, we have the detailed balance condition satisfied, namely pi beta of I, P of ij is equal to P of ji times pi beta of j for equal energy states. These two are the same, these two are the same, therefore their products are the same. Whereas if E of I is less than, say, E of j, what happens? Well, P of ij in this case is equal to Q of ij times pi beta of j divided by pi beta of I. Right? By symmetry of the Q, that's equal to Q of ji pi beta of j divided by pi beta of I. So this is by the symmetry of Q, which Matt doesn't like. But when we talk about the Hastings generalization of this, it'll be a user choice, so we can just make it so. You know, it's only an issue when you're talking about real statistical mechanical systems in a box and all that kind of thing. So, I mean, I don't mean to be sandbagging you or making excuses. It's a very valid question. Okay. This is by symmetry of Q. But what is Q of ji? That's equal to P of ji, because I is a lower energy state than j, and therefore if I propose I starting from j, that's the probability I go there. So because E of I is less than E of j. Thus, what do we have? We have P of ij equals P of ji times pi beta of j divided by pi beta of I. And you just clear the denominator, and you get that again. Pi beta of I, P of ij is equal to P of ji, pi beta of j for all I and j. Well, at least when E of I is less than E of j. And you just do the same argument when E of I is bigger than E of j in reverse, and you get the same thing. So, same argument. When E of I is less than E of j, or bigger than E of j, thus, what do we have? We have it when they're equal, that holds. When E of I is bigger than E of j, or when E of I is less than E of j, that holds. Therefore, we have pi beta of I, P of ij equals P of ji, pi beta of j for all ij in the state space S, and that's the detailed balance conditions. Thus, pi beta is a stationary distribution for this Markov chain, and it's the only one if the Markov chain has an irreducible state space with one positive recurrence class as its manifestation, whatever. Okay, so that is, I mean, this is really a stroke of genius on these guys' parts. And like I said, the paper that they wrote is on anybody's top 20 list in the history of computational science, in the history of heuristic search, in the history of random algorithms. This is the granddaddy of them all, okay? And, you know, regardless of whether you're going to get a handout on this, I'm going to put it up tonight, I think. A handout on this and the generalization I'm going to talk about in a moment, so, you know, don't worry if you don't get all the details of the detail balance or whatever. You know, you'll have a handout on it that's pretty succinct. It's pretty easy to understand. But there's so many benefits of this algorithm that I think it's time to take the 3-minute break, and then I'll talk about those, and maybe you can ask your question. I don't know. Okay. Great.
So if we take away the symmetry, this is just a regular balance condition, not a detailed balance condition, right?
Take away the symmetry.
If we ignore the symmetry on that, this is no longer the detailed balance condition. This is a regular one, rather correct.
I'd have to look at that to answer that properly. I don't know.
And the one from earlier is
Any time you separate into the terms, though, you're running a dangerous, you're playing a dangerous game. Because what you're doing is the balance conditions are one series summed over I equals another sort of trivial series summed over I. The detail balance says if I equate the terms, then we get that to hold. And
so a balance condition is kind of like a membrane around the thing, so everything going in
yeah.
is equivalent to everything going out, right?
Yeah.
It's like a flow.
Yeah, and the detail balance is kind of like, you know, every teeny little area of the membrane has the same flow going, you know,
Everything is the same.
something like that, yeah.
So, okay.
But that's not the... Okay, question from Rahul.
What is the difference between regular, like that distribution, and this pi beta? Is this pi beta dependent on the Boltzmann constant?
Yes, pi beta is the distribution on the discretization that you get by sort of atomizing the Boltzmann distribution.
And then regular is just, you know, whatever other, regular pi is basically where you distribute it on a regular.
If you arbitrarily distribute the initial state as pi of 0 and let the people allot the marbles, you know, that's the way pi evolves. And it's stationary only when the marble allotment stays the same from one step to the next. All right, so anyway, this is a brilliant, like I said, this is a really brilliant tour de force. And, you know, it's so awesome. It's really, I mean, I have nothing but kind of like awe if they thought of this. But let me just run over a couple of the advantages of this. So one big advantage, one big plus for Metropolis algorithm is that it gives a recursive computer-friendly way of drawing points according to pi beta. Quote unquote, drawing a set of points distributed according to pi beta, quote unquote, or quote unquote, approximating E pi beta of f for various f's defined on the state space. Okay, recursive, computer-friendly way of doing this. Very important, okay? And this lies at the core of all modern Markov chain Monte Carlo techniques. And all of the Monte Carlo that people do nowadays essentially is this Markov chain Monte Carlo. So it lies at the core of so-called Markov chain Monte Carlo methods, and I'll have more to say about those in general in a moment. And MCMC is the way that people talk about these things. If you Google on MCMC, I would be willing to bet that the first hit would be Markov chain Monte Carlo. So anybody have the internet up right now? Not on Facebook? Google, Drew always helped me out with this in previous semesters.
Yeah. What's number 4 on Bing?
Bing?
Bing.
Okay. All right, good. Okay, so those are Markov chain Monte Carlo methods. And number 1 on Google, yeah. All right. Bing. Eye roll. Okay. SMH. Isn't that right? Is that SMH? All right, okay, enough of the joke stuff. I noticed last night that I'm a little behind on lectures, and so we're going to have to skip over a couple of things and relegate to handouts that I've done before. But anyway, so this lies at the core of so-called Markov chain Monte Carlo techniques. And there's all kinds of slang that goes along with this. You know, what are some of the user choices here? In just the Metropolis algorithm, it's essentially the Q perturbation, the proposal step. That's a crucial user choice, okay? And we're going to see it manifest itself in the generalization by Hastings of this. But intuitively, what's going on here? If you have only a limited number of possible proposals, given a state you're in now, like you're only perturbing to a very small neighborhood, it might happen that you linger around that neighborhood for a long time if the neighborhood is a local minimum of the energy, right? It might be hard to escape a local minimum. On the other hand, if you have a lot of possible proposals, a big neighborhood over which you're perturbing, then you have a more complex algorithm because the P of ij is going to be less sparse as it happens over the long haul. So what's the trade-off going on here? It's a trade-off between speed of convergence, which is high when you have a lot of motion in the state space and you're exploring a lot, versus complexity, which is also high when you're doing that. Okay, so the proposal step is a user choice, and roughly speaking, big steps correspond roughly to non-sparse Q of ij, which corresponds roughly to high complexity, which also corresponds, and this is bad, but big steps also correspond to speedier convergence, which is good. Okay? So that's your trade-off. That's roughly speaking what your trade-off is, and we'll get more explicit about that when we talk about the Hastings thing, which I'm going to do right now. Okay. So when did Hastings publish his paper? 1970, which was 17 years after Metropolis, Rosenbluth, Teller, and Teller published their paper in 1953. So around 1970, Hastings generalized the Metropolis algorithm. And nowadays, most people talk about Metropolis-Hastings as a hyphenated kind of thing. So that's common terminology. All right, so what's going on here? What is the generalization? Basically, what he said was, hey, you know, Metropolis and company, they were trying to solve problems in statistical mechanics, and statistical mechanics is dangerous, and I don't want to work in statistical mechanics. Therefore, I want to use something Metropolis-like to solve other kinds of problems. So let's forget about that context. It didn't really matter that S in the Metropolis algorithm was a discretization of phase space in stat mech. It didn't really matter that the pi was the Boltzmann distribution. What if S is just some arbitrary Markov chain state space and pi is some arbitrary distribution or whatever? And you want to find a Markov chain that has that as a stationary distribution on the state space. So here's the problem he phrased. Given S a state space, and let's assume it's large and finite, and given a distribution, say pi on S, so it's a probability distribution, non-negative, sum to 1, and let's assume that pi j is positive for all j. So given the state space S and given a distribution pi on S, find me a Markov chain, a homogeneous Markov chain that has pi as its unique stationary distribution. So what I want to do is I want to build a homogeneous, irreducible Markov chain with state space S whose unique stationary distribution, necessarily unique by irreducibility, so whose necessarily unique stationary distribution is this pi. Once I've done that, I can use this to generate populations of points distributed according to pi. I can use it to approximate expected values of functions against the distribution pi, whatever. I can use it the same way I used the Metropolis algorithm when pi was pi beta. Okay, now underlying this is the observation that for a given pi, there are lots of Markov chains that have that as their unique stationary distribution. So note, given a pi, lots of different Markov chains, irreducible Markov chains, have pi as their unique stationary distribution. And we've already actually observed this in a kind of a trivial context. For example, suppose that S is equal to 1, 2. So S is not large, but it is finite. Okay? And pi bar, or pi is equal to 1/2, 1/2. Then for any p in the open interval 0, 1, in fact, even for p equals 0, p equals 1, but whatever, this irreducible Markov chain has that as its unique stationary distribution. It's USD. I'll call it that for one people. And if anyone asks me what USD is in 5 minutes, I will still be here so I can tell you. I told you what it was. Okay, so given pi, lots of Markov chains have pi. All right, so what's Hastings' algorithm solution? You pick any Q that's symmetric and is a transition matrix of a Markov chain. So here's your solution to the problem. First of all, you pick any Q, okay, any Q of ij, where I and j are in the state space S, that satisfies the following two properties. First of all, it's a probability matrix, so Q of ij is non-negative, and the sum over j of q of ij is equal to 1 for all ij in S, or for all I in S. So Q is the transition matrix of a Markov chain, and also it's symmetric. So here we, by fiat, we eliminate the boundary of the box problem. Okay? That's going to be kind of like the proposal queue in Metropolis. Okay? So we're going to define now a Pij, P of ij, by means of the exact formulas that we had in the Metropolis algorithm, except now the pi is going to be this pi we started with rather than the pi beta. So P of ij is equal to Q of ij if pi sub j is bigger than or equal to pi sub I. In other words, if j is a higher probability state than I is, subject to the pi that we want, and P of ij is equal to Q of ij times pi j over pi I if pi j is a lower probability state than pi I. Then it turns out that the Markov chain with p as its transition probabilities has pi as its unique stationary distribution. And if we've chosen q so that this is an irreducible Markov chain, so if we've it turns out that, okay, so if we've chosen q so the quote-unquote q chain is irreducible, that's easy enough, then it turns out that the p chain that we get by doing this thing in item 2 is also irreducible and has the pi we started with as its unique stationary distribution. And I'll write out USD this time. Okay, so you may say, well, how hard is it to choose a Q so that the Q chain is irreducible? Easy. You can make it a random walk if you want. Or you can make it a fully connected Markov chain with tiny probabilities, whatever. It's easy to do that. And any old Q, like I said, provided it's symmetric and provided it leads to an irreducible Markov chain, works. And this follows because from the same argument as we used for Metropolis, namely the detail balance argument. Same exact one as we used before. Okay, so what are the user choices here again? The one user choice you have is the Q. Okay, so let's focus on that. Just like it was for Metropolis, the perturbation, whatever the notion of neighbor. And again, if we can, it turns out, always make Q a random walk, like on the homework problem, in particular sparse. It's not a particularly well-connected Markov chain. Everybody has like just one or two nearest neighbors, or if you can make it a 2D random walk, whatever. But what's going to happen here is, again, Q too sparse is going to lead to slow convergence. of estimates. On the other hand, we can make Q as unsparse as we want. So if we make Q very unsparse, highly connected, Q chain, we're going to have a speedier convergence but much higher complexity. So you have, again, this convergence versus complexity trade-off. And this is a manifestation of something that people call the exploration versus exploitation trade-off in optimization situations. And we talk about genetic algorithms, and when we talk about simulated annealing, we'll see that. Yeah, Drew?
What do you mean by complexity? Like the algorithm?
Yeah, because when you do the Q step, essentially implementing it is going to be, straightforward. But if there's lots of Qs to flip a coin between, right? Given I, there's a lot of Q of ij's that are non-zero, then that's a more complicated probabilistic thing for a computer to do, is choose between, say, 10 to the 37th alternatives rather than choose between 2 or 3 or 4, right? That's why. That's what I meant. Okay, so next time what I want to do is wrap this up and do simulated annealing, which is essentially an optimization application of these ideas.